Hello, my name is Alexander, and in this video I'm going to be talking about my most recent project in autonomous RC car. So what this is, it's an RC car which I built completely from scratch, and it's able to drive completely by itself around a track made of cones, only using the video it gets from a stereo camera. It uses a convolutional neural network to find where the cones are in the camera video, and then it uses two PID controllers to control the speed and the steering of the car. So this is it actually working in action. As you can see, I have the green cones on the left side and then the orange cones on the right side. The reason I do this is so that the car knows that it's going in the right direction. And also sometimes, for example, if the car's turning left, the camera might lose sight of the green cones on the left. So then it knows that it needs to stick to the left of the orange cones on the outside, and it's able to steer in between the gates, and the gates don't have to be perfectly spaced out. The gates can be far from each other, the gates can be wider, and it still works. As you can see here, the gates get pretty wide and it's able to steer completely fine through them. And it also is able to change its speed depending on how hard the turn is. I built the platform myself, so I got a normal RC car. I replaced the motor with a rock crawler motor, so that would be more stable at slow speeds. And I also replaced the servo with something I can control from a computer. Then I have an Arduino on the platform, which is responsible for controlling the motor and the servo. But the Arduino is controlled by Jetson Orin Nano, and the Jetson Orin Nano runs all the neural networks and is basically the main computer of the car. So it gets input from the stereo camera, which I have a Z Mini stereo camera on here, and then it processes that input and then sends signals to the Arduino via serial messages, and then the Arduino controls the speed of the motor and then also the steering angle. So just a quick overview of how the entire system works before I go into more detail. First, it uses a convolutional neural network to find where all the cones are in the image, and it's able to distinguish between green and orange cones. It then gets the closest green cone and the closest orange cone just by finding which mask has the largest area. And then it gets the center between those two cones to basically get the closest gate and then the center of that gate. And then it calculates the angle to that center from where the car is going using projection, and then inputs that number into two PID controllers. One of them controls the steering and the other controls the speed. This is how the convolutional neural network works. It takes in an image of just what the camera sees, which is 372 by 376 pixels. It then shrinks the image in the 9 convolutional layers, and then expands the image again in the 5D convolutional layers. And it also has a skip connection between them so that information isn't lost between the convolutional layers and the deconvolutional layers. And it outputs a mask of 336 pixels by 188 pixels. And in the mask, the black pixels are where there isn't a cone, and then the white pixels are where there is a cone. And also in the white pixels where there is a cone, I differentiate between green or orange by just making the values, if the cone is green, then the value is 0.5. If it's orange, then the value is 1. And to train the neural network, I use cross-entropy loss on a data set which I created. And then also the neural network is run real time on board on the car on the NVIDIA Jetson Orin Nano. There weren't any online pre-made data sets of sort of these types of cones, so I had to make my own. But I didn't want to take a bunch of pictures of actual images with cones in them and then have to manually cut out where all the cones are. So what I did is I just recorded a video of there being no cones anywhere. So I just walked around my house taking video with no cones outside also. Then I took some pictures of cones, cut out the background, and then I made a program which just randomly pastes these cut out images of cones into the video frames that I took at different sizes and positions. And then it would also automatically create the output mask I needed. So as you can see on the right, this is an example of one of the images in my data set. It just has a random image and then these pictures of cones randomly pasted into it. And then you can see the mask where the green cones are gray and then the orange cones are white. like I mentioned before, the neural network uses cross entropy loss, and this is how it works. So the loss is run on every single pixel in the output image, and basically first the function takes an x and y, where x is the output. So for example, if we're just looking at how this function runs on a single pixel, x would be the three values of that single pixel. The first is the percentage that there's nothing in no cone in that pixel. Second is the percentage that there's a orange cone in the pixel, and then third is the percentage that there's a green cone in the pixel. But when the neural network outputs the image, it's not actually in percentages yet. So first, what the function does, as you can see inside the log, it gets the log softmax. So it converts each of those into a percentage. So for example, in x, where I have 0, 4, 1, it would basically, for 4, it would do 4 divided by 0 plus 4 plus 1 to get the percentage of that relative to everything else in that pixel. And once it gets the log softmax, it just puts that into a negative log likelihood. So it takes the log of that percentage and then multiplies it by the target. And the reason we're taking the log, and it's the negative log. So as you can see on the graph on the right, the smaller the output is, the higher the loss is, and it's optimizing the loss. So it will use gradient descent to keep minimizing the loss until it gets to 100% for that pixel. And we're also multiplying by the target, so that if the target is 0, so for example, for x, we only want to optimize it for the middle value, the 4. So 4 would get multiplied by 1, so the loss would actually stay. If, for example, it's trying to optimize 1, 1 would get multiplied by 0, meaning that the loss is 0, so it won't actually optimize that at all. And basically what this cross-entropy loss allows us to do, it'll just keep optimizing every pixel to make sure it goes towards the right value. This is the actual neural network working real time. So as you can see, it sees the green cone as gray on the mask, and then the orange cone as white. And there are some tiny errors with it. For example, when I grabbed the cone, it saw a little bit of orange cone on my hand, but that gets filtered out later in the algorithm because I only focus on the two biggest masks, so any tiny details get filtered out. After the neural network is run on the image and it finds all the cones in the image, it gets the two closest green and orange cone, makes a gate, finds the center point between those two cones, and then it needs to calculate the angle to that center point. And to do that, it's pretty simple. It just uses the pinhole camera model. So if you know the focal length of the camera in pixels, which is just something you can look up for the camera, and then you can get the distance of the difference of the x coordinate of the center of the screen and the x coordinate of the center of the gate. So basically the distance from the center of the screen to that center point of the gate. You can just find the angle pretty easily by doing the arctangent of that distance to the center point divided by the focal length. And that's how you get the angle. So then I can use the angle to steer and change the speed. To actually get a steering angle and target speed in the output, I use two PI controllers, which are just PID controllers, but I didn't use the differential part because I didn't find it necessary. The PI controllers, they input in the angle, which we just calculated, and then it outputs either a steering angle for the steering PI controller or a target speed for the speed PI controller. This is the function for the PI controller where, so P is the proportional gain, and what that does, the larger P is, the more instantaneously the PI controller will act. So for example, for the steering will be a lot more sensitive. If it detects that the angle to the next gate increases, it'll immediately steer there. And the I is the integral gain, and the higher that is, the sort of more smoothly it's going to turn. It might take a little bit longer because what it does is it sums the previous n number of errors. By the way, E is the error. So the integral gain will sum the previous n number of errors So basically, the steering will be a bit more delayed and a bit smoother. So you don't want the integral gain to be too high, otherwise it just won't steer at all. But you also don't want the integral gain to be too small, otherwise the proportional gain will take over and the car will wobble around a lot. This was my first test run, so this was before adjusting any of the P&I values. As you can see, it oversteers a lot, and then it just oversteers out of the track. This is the first working version, so after adjusting the P&I values, I got it to this state where it's able to drive around a lot. This is before I implemented the speed controller, so right now it's just driving at a constant speed. And also, one large issue I have is that it's sticking too close to the inside. And the reason for this is if we look at what the camera's seeing, I didn't think about this when I was making it, but when it turns left, the camera loses sight of the cones on the inside. So then it's kind of just turning the maximum angle to the left until it does find a green cone, which kind of works here, but it sticks really close to the green cones to the point where the wheels are sometimes driving on top of the base of the green cones. So that's an issue that needs to be solved, and I need to implement the speed controller. To fix the issue with it sticking too close to the inside, what I decided to do is calculate the distance. When it doesn't see a cone on the inside, it calculates the distance to the cone on the outside, and then sets the center point, the point that the car is aiming towards, about half a meter away from the outside cone. And to do that, I need to calculate the distance to the outside cone. I don't actually use the depth on the stereo camera because it wasn't too stable. But since all the cones are the same and I know their height, I can calculate the distance to the cone using inverse projection. So this is sort of a diagram. So I know I know the focal length in pixels of the camera, and I can also find the height in pixels of the cone on the camera using my masks. I then know the height of the cones, which is capital H, of the cones in meters. And then I can, just using proportions, I know that the distance to the cone in meters divided by the focal length in pixels is equal to the height of the cone in meters divided by the height of the cone in pixels. And then I can just multiply each side by the focal length, and I get that the distance to the cone is the focal length times the height of the cone in meters divided by the height of the cone in pixels. And then when I have the height, when I have the distance of the cone in meters, I'm able to use that information to calculate about how many pixels half a meter is to the left or to the right of that cone. And this is the sort of improved gate detection. So now, as you can see, when it doesn't see the inside cones, it doesn't draw a line, but it just draws the dot of about half a meter away from the outside cone. And it works pretty well. After fixing the steering, I just created another PI controller to control the speed, which wasn't difficult. I just, again, inputted the angle and then it outputted the speed. I adjusted the P&I values until I liked how it worked, and I got this. So this is the final version. As you can see, it's steering completely fine through all the gates and it's changing its speed. This is another good video of the final working version, and this is in a garage where the walls are both orange and green, so it was a good stress test for the neural network to see if it would go insane when it saw all these orange and green walls. But the car is able to drive here completely fine, and the speed's able to change really well. And yeah, thank you for watching. I will leave a link to the GitHub project for this RC car in the comments section below. And yeah, thank you for watching.